Okay, so we have another related rates problem. A camera is placed on a tripod 10 feet from the side of the road. The camera is to turn to track a car that's driving by at 100 miles per hour for a promotional vehicle or promotional video. The video's planners want to know what kind of motor the tripod should be equipped with in order to properly track the car as it passes by. So how fast must the camera be able to track the car? So we've got a highway here, and then we're going to set up a camera along the side of the road, and the camera is going to be 10 feet away from the road. Okay. We've also got a car, and it's traveling this way. And so what we want to know is how fast the camera has to be in order to track the car as it's moving. Okay, so the camera is 10 feet away from the road. This X distance opposite from this camera here is actually shrinking, okay? And then this angle theta represents where the car is, the angle with respect to the camera that it has to shoot out to get to the car. Okay, so the car is traveling at 100 miles per hour to the right. So as we go to the right, the value of x is actually getting smaller. It's decreasing. Okay, so dx dt, the derivative of x with respect to time, should be negative since we're shrinking as time passes. Okay, remember the car is getting closer and closer this way. Okay, and so turns out the fastest time in which we are actually turning is as the car is passing at a perpendicular straight through right there. Okay, so the car is actually, the angle that the camera is having to turn is actually slow. It's speeding up, and then it gets super fast. This is the fastest that it has to turn at that point right there. Okay? So, number one, what do we want to know? What do we want to find out? We want to find out how fast the camera can turn on the track. So we seek information about how fast theta is changing. Okay, if we figure out the change in theta, then we know how fast the camera needs to be able to turn. So that's d theta dt. Okay, that's what we're looking for. Now that we know what we're looking for, let's write down everything that we do know. Okay, well, we know that dx dt is 100 miles per hour. Now, why is it negative? The rate is negative because as we're traveling in this direction, my x value is getting smaller. Okay, so x is decreasing. So I'm traveling at a rate of 100 miles per hour. That's what I'm getting given here. And so what I need to do is I need to do some unit conversions. I need to convert my miles per hour into feet per second. Okay, so when I'm talking about my angle, everything needs to be in the correct units. Okay, so in order to convert this, we got to use conversions here. So to get rid of hours, I'm going to convert that to minutes. And to get rid of minutes, I'm going to convert that to seconds. Okay. Now I need to get rid of miles. Well, what do I know? There's 5,280 feet in 1 mile, so that's going to cancel my miles units. So I need to multiply negative 100 times 5,280, divide by 60, divide by 60. And when I do that math, I get negative 146.6666, repeating, right? Feet per second. So now I've converted from miles per hour to feet per second. Okay? So part of these problems is making sure we have the correct units. Okay, so number 3, now what do? I need to have an equation that is relating theta with the position of the camera. Okay, the position of the camera. I need to have it relating with the speed, okay? So the speed, how fast that the car is traveling, so dx dt. I need to have it relating with the position of the car, so where x is located. And so 10 here, position of the camera, how far we are away from the road. So I need something that relates all of these things here, okay? Now if I have an angle and I have the opposite side and the adjacent side, I should be thinking right angle trigonometry, okay? So an equation that relates all these things together is tangent of theta. Tangent of theta is opposite divided by adjacent, 10 feet, okay? So I'm going to take the derivative, step 4, take the derivative with respect to t. So the derivative of tangent of stuff is secant squared of stuff times the derivative of the stuff d theta dt. Okay, and then derivative of x with respect to t is dx dt, and I keep the constant the same. So now I have my equation that relates position of the camera, the speed, and the position of the car. So I'm going to take this, and since I want d theta dt, I'm going to solve by dividing both sides by secant squared theta. Now, one thing I'll hope that you recognize from trigonometry, if dividing by secant squared theta is the same as multiplying by the cosine squared of theta. Why? Because they're reciprocals. Remember, cosine theta is 1 over secant theta, right? So cosine squared is 1 over secant squared. Okay. So now, number 5, I'm going to take all the information I have from the first couple of parts, and I'm going to plug it into my derivative equation. So what do I want? All right, I want cosine of theta, and I'm going to plug in a dx dt here. Now, the dx dt is no biggie. It's the theta. What is the theta that maximizes the speed of the angle, right? So the question is, we want to know the fastest the camera needs to turn, because if I'm trying to figure out how fast the camera needs to be able to turn, then I need to know the fastest speed at which the car is passing the camera and it's making the change in the angle go quicker. And if you'll recall, the closer and closer the car gets to, hold on a second, let me see if I can do something clever here. Oh no, that's not going to work. Okay, so just pretend that the car is on the end of this little stick right here. And so as the car gets closer and closer here, what's happening? The rate of change of theta is changing. So you can see, if you just focus for a second your eyes right here on this part here, and watch how the side changes kind of slow, and then it really speeds up towards the end, right? I'm not changing the speed that I'm traveling over here. I'm just slowly, going through like this. And you see, as we get into here, it starts collapsing really fast compared with going, here to here. It's the angle theta is not changing that much. But whenever I go here to here, the angle theta is changing really quickly, okay? So the angle theta is changing the quickest whenever we were at a perpendicular distance away. So what theta would that be equal to? Well, that would be when the car is directly in front of the camera, and the biggest value that cosine of theta could possibly be. Remember, cosine theta is stuck between 1 and -1, right? So the largest that you could make cosine squared theta would be 1 squared, which is 1, okay? So the biggest, the fastest you can make this is equal to 1, right? So no matter what cosine or theta angle you put in there, 1 is the largest that would be. This occurs when theta is equal to 0. Okay, so I'm going to take 146.667 and the feet, and it's negative. Remember, the negative sign tells us that the camera is rotating in a counterclockwise fashion. Okay, so counterclockwise, remember clockwise is like this, right? And counterclockwise would be the opposite direction, right? So we're rotating in the opposite direction, okay? Now the feet cancel, and so what do I have? I've got moved the decimal over one place because you're dividing here by 10, and this is in radians per second. Now remember, a radian has to do with the arc length, right? And so to figure out your revolutions per second, you need to take that number and divide by 2 pi, okay? So if you're having trouble with it, go back to the pre-cal videos where we talk about revolutions, okay? So when we talk about revolutions in turning a wheel, we talk about this concept here. Okay, so this ends up being 2.33 revolutions per second, and technically that should be a negative 2.33 right there. Okay, signifying you're going in the clockwise fashion. Okay, so negative sign tells us that you're rotating the camera clockwise and not counterclockwise. Typically, when you're talking about rotating around a circle, you rotate in the counterclockwise, but if it's negative, you go in the clockwise. Okay?